you've probably heard some sort of a meme of like everything is a multisig, every bridge is a multisig, and this is like terrible security.
You know that one of the attacks potentially to doing a cross-chain transaction too quickly is if the source chain reorgs and that deposit transaction is no longer included, then
Just because something says that they're secured by a TEE, if you have to like, you really should go look at their code, and their code running in the TEE still needs to be audited for bugs.
when you are considering the security model that you choose for your application, I hope this podcast could help. From Alysia Tech and Ellie Davidson, welcome to Composable, a podcast that takes you deep into the tech behind Web3's building blocks.
Every episode, we dive into one key question about how crypto works today and the design space for how it might look in the future.
Composable is an Espresso pod, a production of Espresso Systems. All opinions expressed by Composable's hosts and podcast guests are solely their own views. This podcast is for informational purposes only and should not be taken as investment, legal, or technical advice.
And today, we're going to be talking about who secures cross-chain messages. So this is kind of one of those things, you're bridging something, doing all of these things between L2s. Like what actually secures all of these things that are communicating? What actually secures bridges? That's what we're going to dive into today. And we'll kind of compare, contrast, the different security approaches.
And to start, we're going to talk about some bridge attacks to talk about why this is relevant. So in 2024, there was a Ronin bridge attack. And essentially what happened with this attack is that they performed an upgrade, which is something you can do with smart contracts. But when they performed this upgrade, they forgot to reinitialize the voting threshold. So the voting threshold was a default, which was 0. So that means the attacker was able to allow a transaction to proceed, which no one voted on. But because the voting threshold was set at 0, the attack went through. What do you think about this attack, Ellie?
So this is one of those attacks where like I can feel two sides of it, because on one hand you're like, okay, that's like a really silly mistake to make, but then on the other hand, I kind of get it sometimes, like, you forget to like initialize something. But I guess this is like one of those things where you need like scripts to deploy your stuff and make sure that they work, and so you deploy it all the same way every single time. But I can feel for Ronin.
Yeah. I think in this case, they were able to recover a lot of the funds. But it's interesting because like you have your code that's audited. Let's say their verification contract was 100% sound. They performed an upgrade, which is probably something they don't do a lot of. Maybe their upgrade scripts weren't audited. Maybe they were, not sure. But it's like an edge case scenario where you don't expect it to happen. And it's really just like an operational security error, I would say.
Yeah.
Yeah, because upgrades in Web3 is not like a routine process. Like
Mhm.
technically, some contracts aren't even upgradable. So I can't even imagine there's really amazing infrastructure available to ensure that you have the smoothest upgrade possible. So yeah,
Mhm.
it's one of those things that could happen, but definitely very unfortunate, but also
Yeah.
just shows you that cross-chain messages need a lot of security. Blockchain and technology in general, yes, but cross-chain for sure.
Mhm.
So this is a big one, probably
Yeah.
one of the biggest.
I remember, yeah, when this happened, this was when I was like first kind of getting into Solana a little bit.
Yeah.
And then this happened.
Oh my gosh. Were you using Wormhole at this time?
I wasn't, luckily, but I was going to. Like, I had planned to totally bridge my funds to Solana using Wormhole. Like, I think this happened like a couple of days before I was like, oh, like I guess I better not do that.
Yeah. I think I used them, but maybe for a very small amount. So I'm not even sure if I was affected. But essentially, Wormhole was one of the first bridges, if I remember correctly, to allow you to bridge from Ethereum to Solana. So
Mhm.
what would happen is if you want to bridge, you would lock up your funds on Ethereum, as you know with bridging, if you listen to our previous episodes. And then those funds would be released on Solana as a new token called RAT-ETH. So normally how it works is that Wormhole was depending on a set of off-chain validators, or I think they were calling them guardians, for the purpose of just verifying these transactions. And normally what they will do is they will sign a message saying like, yes, this is valid. We all observe that the person actually did deposit these assets on the Ethereum blockchain. But the issue in this one was that they did have the verification logic, but apparently one of the functions, there was a bug. And because there was a bug on this function, the attacker was able to forge a proof, which made it seem as though he or she deposited 120,000 ETH on Ethereum, when in fact they didn't. And because the validation logic on the Solana blockchain saw it and was like, oh, yeah, this is correct, sure, do your thing, they were able to then mint 120,000 wrapped ETH, which didn't actually exist, as in, like, they didn't actually lock it on the source chain. And yeah, that's how they were able to perform this attack. So definitely a lot more sophisticated than the previous one.
Yeah, I think if I remember correctly, as an engineer, I can feel this because I think the attack was through a deprecated function, like
Mhm.
call using a library. And it's kind of one of those things like, yes, you shouldn't use deprecated functions, but also sometimes it does take a long time to go through your code and like update things. And
Yeah.
yeah, it's just all very, very tricky. But yeah, this one was a lot more sophisticated for sure.
Yeah, and the thing is, like, at the point in time when you write your code, it wasn't deprecated, I would assume.
Mhm.
So,
Yeah.
and you could argue like you shouldn't have upgradable contracts like we saw in the previous attack. They were able to, like, they didn't
Mhm.
upgrade, but the process wasn't sound. And as a result, it left a vulnerability. But in this case, if the contract was not upgradable, now you have a deprecated contract because some
Yeah.
cryptographer realized, like, you know what, this is vulnerable. And then you're not able to fix it. So you
Mhm.
have to be able to have upgradability as well. So yeah, that one was unfortunate, but it was a big one. So it definitely it
Yeah.
definitely left a splash. And I'm not sure how much of it they were able to recover. The good thing with some of these attacks, like, you are able to recover some of the funds because what they
Mhm.
tend to do, like this particular one, let me put it on screen. I think Orbit did this, or I might be wrong. But essentially, what they do is like when they have an attack, they would then say, hey guys, like, could you please return some of the funds? We will call you a white hat hacker.
Oh,
And I
yes, you're
believe,
right.
was it Orbit? I think like they gave out NFTs with like white hats. They were like, if you were to get this money back,
Mhm.
it's so crazy. But like, yeah. Because I guess everything is public, right? But anyway.
Mhm. Yeah, I think okay, this is, like, based on pure memory, this could be totally wrong, but I think when the
Yeah.
wormhole, hack happened, there was, like I remember seeing on, like, Twitter, people being like, "Hey, if this was you, like, return, like, 90% of the funds, and we'll let you keep, like, the other 10%," or yeah.
Yeah. I've even seen people say stuff like, "Oh, if we all attack, then they can't, like, they can't penalize all of us. So like we should all
Mhm,
attack it." And it's like, no, that's not the logic. But yeah, with Orbit, this one is a bit different. So this one was like really confuses me. And like from the research I did so far, like I wasn't able to figure out how exactly it happened. But essentially, they did have like a multi-sig validator set, again, collecting signatures, normally based on a threshold. So let's say 3 out of 5. And if 3 out of 5 of those validators sign, then boom, the transaction has been verified. In this case, somehow the attacker was able to get the private keys and sign transactions that weren't real. So I have no idea how that would have happened because technically your validators are supposed to be super distributed. So maybe they were all targeted via a phishing attack. Maybe it wasn't that distributed. Maybe there was one DevOps guy who was in
mhm.
control of the keys. No idea. It's not clear, but yeah, that's how this attack happened.
Yeah, I think this is a good attack, well, this will come up in our discussions later on, so it's a
Yeah.
good, precursor to that, but, yeah, it's that, you're only as secure as, like, your DevOps and your operational security, and that doesn't necessarily equal the same amount that you have staked somewhere. Like, I don't think this was the case in Orbit, but let's say Orbit, bridge, was vulnerable. Like, they could be slashed for doing something wrong. Well, that doesn't
Yeah.
actually give you, like, $1 billion of economic security if, like, they're only paying their OPSEC team, like, you know, 100K. Like, you actually have 100K worth of economic security because someone can hack you.
Yeah, yeah, for sure. And I think a lot of these protocols, they do have bug bounties for that reason. Like they have these massive
Mhm,
bounties so that if you were to see a vulnerability, they're trying to incentivize you to just take the bounty, produce the error to them instead of actually executing it. And in some cases, what they will do is like if there was an attack, they will try to pay the bounty amount to the attacker. So like let's say they got
mhm.
millions, they're like, hey guys, if you keep 500K and send the rest, you're good.
Yeah. Mhm,
But if we think about like what happened with these attacks, like it just shows various ways in which a cross-chain message could be insecure. It could be that the verification logic is not sound. It could be because either there is a genuine bug or a function becomes deprecated because a bug is eventually found. It could be that the actual logic for verifying that all the validators agree So these are off-chain validators. They all agree that the transaction is valid. Maybe that could have a flaw as well. So we'll try to go over some of the ways in which, you can verify cross-chain messages, what is even happening when you have a cross-chain message. But I think overall, what this should drive the point of is when you have a cross-chain message, it's no longer native to the blockchains. Like we have to work with various systems to verify that it's valid because it's one ecosystem going to another ecosystem.
All right. Yeah. So, Alysia, do you want to dive into the anatomy of a cross-chain message?
Yeah, let's go. So, nothing surprising here. We have a user and they would like to transact something from chain A to chain B. If we talk about a bridging transaction, that means they're probably locking up ETH on one chain and then minting it on a destination chain. So, they try to send that message, and there's like some entity in this diagram, I'm calling it an observer. And this entity notices, like, hey, we have someone who has deposited ETH into a particular contract on chain A, and then they would have to try to generate a proof to prove that that's valid and then submit it to chain B. And on chain B, this could be on chain or not, there's some level of verification that checks to see whether this indeed happened on chain A. Obviously, chain B doesn't know anything about chain A, so it's 100% relying on that proof and its verification logic. And then once the verification logic passes, then we can say, yes, this person can receive this wrapped ETH on their destination chain, which is chain B.
All right. So, well, let's dive into where can trust be broken. So, this isn't a live stream, but this would have been fun to have people give us ideas about like where trust can be broken in this model.
Yeah.
The answer is that it can be broken in a lot of places, which we're going to go through right now.
Yeah.
So overall, I would say that trust can be broken in kind of two categories of places. One is in the cross-chain message part, where
Mhm.
whoever is supposed to be verifying this message lied about the message somehow. And then the other part is that you can just have bugs in your smart contract that allow people to do stuff they aren't supposed to.
Yeah.
Um,
100.
yeah. All right, so let's go through a couple of different kinds of ways people validate cross-chain messages. So the first one, which I'm sure a lot of people have heard of, are multisigs. And so multisigs are just a group of validators, and they all sign some attestation of what happened on the source chain, and then they post this attestation to the destination chain. Now, multi-sigs can like vary a lot. So, for example, you could have a 1 out of 2 multi-sig, which means that you only have 2 validators that are even part of the system, and you only need one of them to submit a message to the destination chain for you to trust it. You could also have a multi-sig that is like 30 out of 40. And so, this requires a lot more coordination among the validators, but you have a lot more diversity. So, in general, multi-sigs that are bigger are going to be more secure. But that assumes that, your multi-sig validators are actually diverse and not just like all the same person running 40 different instances. Um, so yeah. All right. So yeah, that's the multi-sig. And your trust assumptions here are there's a lot of them. So one, you have to when the multi-sig validators receive the information of what happened on the source chain, you have to
Mhm.
trust that information is true. So a lot of the times the way you trust it is you just wait for finality, or you wait for that rollup to settle on Ethereum, which takes a long time, but you know that the data coming from that rollup is true. Other sometimes multi-sigs will just trust like a sequencer confirmation, which is very fast, but the sequencer could actually lie about that and you don't really have any recourse. So
Yeah.
first you have to trust the source of the data that the validators of the multi-sig are reading from. And then you have to trust that the multi-sig is honest. So you have to trust that it has enough of an honest majority such that no invalid signature could ever be signed. So, for example, if you only have a 1 out of 2 multi-sig, you have to trust that both of those validators are honest because one could just lie and that would verify the message. Whereas if you had a 3 out of 5 multi-sig, you don't necessarily have to trust all 5 of the multi-sig validators. So, yeah, you have to trust the validators. You have to trust the source where their data comes from. And then you need to trust the proof system slash the smart contract that validates this. And this is basically saying like, okay, my proof system doesn't have bugs in it, my smart contract doesn't have bugs in it, etc. So I'd say that those are the three kind of trust points with a multisig. And well, I personally have a lot of opinions about multisigs. I don't know if we can go into those now, or maybe we can discuss them later.
Yeah, go into it.
All right, let's go into them now. So if you kind of are on crypto Twitter or kind of part of the space, you've probably heard some sort of a meme of like everything is a multi-sig, every bridge is a multi-sig, and this is like terrible security. So let's dive into that a little bit. It's generally true. Multi-sigs generally aren't the best ways to do things, but it's nuanced. Like I said earlier, it really depends on how large your multi-sig is and who is in your multi-sig. So I will actually say like Axelar and Wormhole, like they do this where you could consider them a multi-sig of sorts, maybe more Wormhole than Axelar, but they have really big committees of like a lot of validators. And so that makes them quite secure because these are like diverse. You can go, I'm sure, look up online and see like where these node operators are, etc. So that's pretty good. Um, but I would also like to mention in that case that you still have to trust the source of where the data is coming from. So even if a validator is honest, if someone lied to them about the blockchain's data that they're like reading from, then they'll still sign something that's invalid.
Mhm.
So there's a couple. Yeah, so I guess to summarize, a lot of bridges today are multi-sigs. And to be honest, a lot of smart contracts today are multi-sigs as well, in that, a multi-sig can upgrade the contract arbitrarily.
Yeah,
And um, I don't want to be too down on them, but there's trade-offs. Generally, I want us to move away from multi-sigs, especially small ones. A
right.
multi-sig like under 10 or something we should move away from, in my opinion, long term.
Yeah.
But they have been a suitable stopgap, to kind of balance user experience and get fast message passing compared to some other models. But anyway, what do you think about multi-sigs?
Yeah, yeah. Okay, so but for me with multi-sigs, I think I like when something is practical. And I like that it gets us to the solution where it's fast, like having an on-chain signature via multi-sig and even verifying that signature is very fast because we're using a lot of like the cryptography that we're already using in the blockchain space as well, compared to some other solutions, which we will discuss. I think even when you were mentioning what can make, like, what are some of the touch points when it comes to multi-sig and what makes it vulnerable, are things that exist for any system, I believe. For example, if you are getting a bad data source, you're trusting the data. Whether you're using a multi-sig signature or a ZK proof, you have to make sure the data source is valid. And then on the verification side, yes, even if you're using a ZK proof, for example, we need to make sure that that code is bug free. So I would say on both sides, like, yes, obviously a ZK proof verification might be different from how you're doing the verification for the multi-sig for sure. So there could be more complexity there. But those are constants, but definitely the mechanism in between and how spoofable it is and how easy it is to undermine it is where we have issue. And I think the reason why multi-sig gets so much flack is because private keys are so easy to be lost or stolen.
Going back to the orbit hack that we talked about earlier.
Yeah,
Yeah.
exactly. Like, it's so much
Mhm.
harder for you to forge. At least I would think so, unless the verification logic is buggy. And again, that is a constant across all verification. You need to have like bug-free verification logic. But it's so much harder to spoof a ZK proof compared
Mhm.
to do a phishing attack, pretend to be someone, get their private
Yeah.
keys. Like, like that's just, and I think that's the reason why people come down on it. But of course, like, there are ways to remedy it, like you mentioned, having a large enough validator set. And I think that's another thing that's a little frustrating, is that it's not very public how many people are in a multi-sig or how
Yeah.
distributed it is. So you as a user, like, that there are many protocols behind multi-sig and multi-sigs are getting so much flack. But what if this protocol actually has a validator set of like 100 out of 120? Like,
Mhm.
you would not know, and also you don't know where they're located. Because if they're
Yeah.
all 100 private keys owned by one DevOps guy, then that's not
Mhm.
great. By the way, I'm not picking on DevOps
No,
people.
not at all. In
um,
general, I think that this shows that, like, people should pay DevOps and operational security people more because there's a lot at stake if they don't do their job well.
Yeah, for sure.
Mhm.
So if you're doing multi-sigs right, like, you should not have this issue. So again, it's kind of like down to a user error again, like if you're just
Mhm.
making certain assumptions that aren't correct. So maybe the future of multisigs is that there's a way to do multisigs that makes it harder for you to do multisigs wrong. And then you
Mhm.
can trust it a bit more. And also maybe a little bit more transparency around your multisig and who's involved.
Yeah, I completely agree. And so there's also another attack vector. This isn't really a safety issue, but a liveness issue. If um, your multisig is 1 out of 2, let's say, you have
Mhm.
to rely that at least one of those validators is actually online. And this
Right.
might be totally fine if it's a professional operator who knows what they're doing. But
Yeah.
if they go offline and they crash, your cross-chain message might just never get delivered, and your funds are just kind of stuck in this ephemeral bridge in the middle. So it's not quite as serious as a safety attack, but it's still
Yeah.
something that can happen.
No, yeah, that's very valid. I'm glad you mentioned that because even though you were not benefiting, the attacker, let's say they were somehow able to bring down a multi-sig, like they're not benefiting because they're not getting funds. But if you deposited your assets and it's just locked in this contract and you're not
Mhm.
able to redeem it, or your protocol is not working as expected, that is still a bad situation to be in.
Yeah. All right, so we did multisigs as a way to verify cross-chain messages.
Yeah.
I'm actually going to talk about TEEs next because they can kind of be thought of as an extension of a multisig. So a
Okay.
TEE is a trusted execution environment, which is basically a piece of hardware that is very specially designed so that it's isolated from other parts of the machine. And the point of this is that you can run code in this isolated environment and you can trust that no one can tamper with it. So, for example, on a normal computer, someone could, for example, tamper with your storage. They could say, oh, you stored that your bridge has 100 ETH. Well, I'm actually going to say it has a million ETH in it.
Right.
So that could happen. And a TEE uses hardware to prevent this from happening. The most popular TEE people may have heard of is Intel's SGX. There's also TDX, and there's also AWS Nitro, among some others. But they've become a lot more popular lately, especially over the past year. Kind of, especially I think Flashbots has been really kind of leading the charge of TEEs, which I think is really good. Um, but okay, so how do TEEs affect this whole like cross-chain message verification? So what a TEE does is that it runs some code that you tell it to, and then it makes this attestation, and this attestation is signed by a key that you can verify is only usable by the TEE. So if you have this attestation and you trust the underlying hardware of the TEE, you can be sure that the exact code that you expected was run. And so this kind of fixes the problem of the um, validators in a multisig lying. So, for example, let's say we took our multisig, but we made all of the validators run inside of a TEE. Like, does this actually give us any better security? Yes and no. It fixes some things, but not other things. So it does fix the ability for the validators to just lie, to just, say, oh, yeah, someone deposited 100 ETH, even though they didn't. Because you have the TEE code that can only run the code you specify, and the code you specify presumably says you can't lie about 100 ETH. Um, so it does fix that for sure. But it still leaves some gaps. And I think that these are kind of nuanced where sometimes we think like, oh, TEEs or ZK proofs will just solve all of our problems, and it doesn't quite. So, like we said earlier, the data that the TEE reads in to verify the state of the source chain, it still has to be real. So if you give the TEE data of, the source chain that didn't happen, it can still run the code, produce a valid like attestation, but that it'll be incorrect. So I think a really like key point I want to drive home is that you need to make sure the source of your data is valid, because your security basically doesn't matter at all if you know you're inputting false data. So TEEs are still susceptible to that attack,
Yeah.
and TEEs are they're still susceptible to a liveness attack. So, for example, if you have a small multisig, even if they're all running in TEEs, running a TEE does not necessarily give you any more liveness than not. So you still have that issue. And then you do still have the issue of bugs. And particularly, I want to notice the bugs in the TEE. So the TEE will run whatever code you tell it to, and it'll sign an attestation. But if the code that you tell it to run has bugs in it, obviously that's not going to work. Anyway, so the point of this is that multisigs that require all of their validators to run TEEs definitely help security quite a bit, in my opinion, but they do not solve for the entire problem. And that's like the big point I want to make, kind of hammer home.
Yeah. Wow. TEEs. I remember we were at Bangkok, was it?
Yeah.
And literally there was a presentation where they started off like, oh yeah, just put this one thing in a TEE. And they just kept going and going till they're like, oh, the entire thing is just everything in a TEE.
Yeah, I feel
Okay.
like now on
Yeah.
crypto Twitter, it's like a meme, where it's just like, "Oh, you have a problem with your design, just like throw a TEE in there, it'll fix it." Which
Yeah.
sometimes is true, to be fair, but not all the time.
Okay, so I want to like use this diagram, and if you are listening on the podcast, like definitely check out the video stream of this, which will be on YouTube and Twitter. But you're saying that okay, the TE is now responsible for generating this proof that I have seen the data. I saw that the user locked the assets on the source chain, and I'm going to create an attestation that verifies that. And then
Mhm,
the destination chain, in this case, chain B, this destination chain is then able to verify that this particular transaction was indeed attested by a TEE. So the verification on chain B is not did the user lock the assets on chain A. The verification is did the TEE that we expect to sign this transaction actually did,
mhm.
present this attestation. Would you say that's accurate?
Yes, that's accurate. But actually, this brings up a kind of a cool nuance of what you said is that it has to be signed by the TEE you expect. So that's another
Right.
part. Sometimes people do break TEEs and they break their hardware, and sometimes there are TEEs out there that you cannot trust to produce a correct attestation. So you need to make sure that the TEE who's sending you these proofs, has
Yeah.
not been denied or like blacklisted somewhere as a bad TEE. So yeah.
Interesting. Right, because I'm thinking like, is it possible for someone to generate a fake attestation? So basically spoofing the logic, just like you can spoof some other proof logic in another type of system. And then in chain B, is there a way for chain B, I'm wondering, to verify that the TE read from the data source you expect? Like, what if we just tell you
Mm,
that's what the TE is doing? We
yeah.
as like the protocol developers. But what if the TE is just verifying that 2 + 2 is 4?
I mean, yeah, exactly. No, yeah, and like this is kind of why actually looking at code is important, which I'll be first to admit it. Do I go and read a lot of the code of the crypto stuff I do? No, I don't.
Yeah.
But yeah, it's like just because something says that they're secured by a TEE, if you have to like you really should go look at their code and their code running in the TEE still needs to be audited for bugs. Like
Yeah.
running a TEE doesn't, get rid of the need for auditing and, designing safe code.
Yeah, I agree. I want to just quickly compare this to like let's say you had a validator set and they signed a multi-sig, so you had to get a threshold of signatures. And I'm
Mhm.
just trying to think about how it can be different. So in both cases, you're expecting that all of these validators indeed read from the correct data source. And if they are reading from the correct data source and checking out for things like finality times, they're then able to sign a transaction that they think is valid. And but in the same case, that's what we are expecting of the TE. We expect the TE signs a transaction or creates an attestation for only valid transactions. I
Mhm.
think in both scenarios, there are vulnerabilities that can happen. So, for example, we saw the private key can be lost or someone steals it.
Mhm.
And then in the case of a TE, it's not complete the research. Like I have heard about ways that you can spoof a TE attestation, but potentially, if we had staking involved in both scenario and the other scenario, maybe that could help a bit because if you have skin in the game, there's less likely that you'd read a transaction
Mhm.
that is not real and then sign off on it. But I don't know how that works for TEs, but I'm just like thinking
Mhm.
live right now.
No, like, that's a really, really good point. Yeah, if the validators in a multisig, even if they're running TEEs, had to stake and, they got slashed for doing something wrong, I think that does help security, right? Because
Yeah.
then you have punishment for doing something wrong, whereas in a lot of multisigs today, if they would do something wrong, they really don't have any punishment other than maybe people don't trust them in the future, but,
Yeah.
no, yeah, it's very, very true. Mm,
Yeah. But then, of course, you're still assuming a majority on a set. So there's that.
yeah. Mhm.
Because if all of the keys from or majority of the keys from the multi-sig get stolen, then who's going to tell you that's a flashable event?
Yeah, exactly. Mhm.
And I guess like another solution, which we'll touch on briefly, is ZK proofs. So with ZK proofs, you're going to have on-chain verification, and in chain B, it's actually going to attest that the transaction did happen on chain A. So it would need to have enough data about chain A's state to be able to say, like, yeah, I actually do see this in chain A's state. Still, like as Ellie said, the data source has to be valid. If for some reason not the correct data source is sent over, then it can still be vulnerable. But at least we don't have to think about a private key being stolen because a ZK proof is on chain. Of course, we still have to think about the verification logic and if there are bugs. But yeah, if there are bugs in the verification logic, then a spoof would work. So yeah, the data source and the verification logic tend to be the two places that need to be very solid. And then once those are solid, then the options are like more like operational security. How easy is it to break into a TEE? How easy is it to like spoof and fish and get private keys?
Yeah. Mhm. I mean, I think most people kind of view ZK proofs as like the best option. And I would agree, generally speaking. We don't see a whole lot of bugs in ZK proof systems, but like there are actually. I just think a lot of them aren't found yet or they aren't popularized. So the ZK proof systems are not perfect because, like all code, they have bugs in them. But yes, generally a ZK proof is going to be one of the most secure things that you can do to secure your cross-chain messages.
Yeah.
Well, okay, then, Alysia, why don't we all use ZK proofs to secure our cross-chain messages?
Right? I mean, like ZK proofs tend to be expensive to execute. Like the ZK proof logic is cryptography as well, just like a lot of the verification systems in the blockchain space. But we can see with various chains, like I remember I used to try to create ZK apps on a protocol called Mina. Loved it. That's how I learned about ZK. But then you realize like the proving time, it does take a long time. And I think that if your transaction is very time sensitive, that will not be great, which is why I'm actually such a fan of customizable security models, which we will touch on later. Because if a system does require that level of security, then I will be willing to wait 3 minutes, let's say, for a ZK
Mhm.
proof to transact.
Yeah, completely. All right, what should we touch on next? Oh, let's touch briefly on light clients. So, people may have heard of light clients. What is a light client? It's basically something that runs on the destination chain that verifies the source chain. So what a light client, it would be, for example, it's a smart contract on the destination chain, and you send it data from the source chain that you need to make sure that data is like actually valid. But you send it data, and then on the destination chain, it'll verify like some proof, usually a Merkle proof, that proves that some transaction was included, that some bridge event actually happened. So clients are they can also be very, very useful. The issues with them are sometimes they can be quite expensive, kind of like ZK proofs. Sometimes it's very expensive to verify another chain's data. So, for example, let's say I want to verify rollup A's data on rollup B, but rollup A is a ZK proof. That means I need to verify a ZK proof in this smart contract on rollup B. And that might get expensive if you have to do it all of the time.
Yeah.
But other than that, light clients are probably one of the better options that you can go with. So like IBC which is a very popular messaging protocol between chains in the Cosmos ecosystem. It relies on light clients. Um, yeah, I'd say that light clients and ZK proofs are fairly close in security. It's not really, you can't really say which one's like better than the other because they're different. But I'd say that they're fairly close.
Yeah.
But again, you might have noticed this is a common theme. It relies on the source data being honest. So this is why a lot of light clients wait for full finality of the other chain. So a light client on chain B will wait until chain A has settled to Ethereum first before reading in data because it needs to know that that data is valid.
Yeah.
And that's slow, obviously. But anyway, yeah, I just want to like drive home the common theme that none of your proof systems matter if the data that you give it from the source chain isn't the real data from the source chain.
Yeah, totally agree. And I think that also makes sense, that point that you mentioned, which is that it has to wait for finality, especially with light client verification and ZK proof verification, because it's happening on chain. So once that message has been sent across, which can be sent across almost immediately, but it has to wait for finality, it will then execute as soon as it's verified. Whereas if you did have some kind of off-chain verification, maybe you can do other things like slashing, for example, to prevent bad behavior. So maybe if they decided to wait or not wait for finality, they're in
Mhm.
a better position to do so because the verification happens offline. So they can just have like a different model, which is what we will see with things like layer zero and hyperlane, where you can customize like things like how many confirmations you want to wait for before you say a transaction is at least final in your books.
That's a really good segue. Should we start talking about layer 0 and Hyperlane?
Yeah, sure. With layer zero. So again, you have two chains and you want to send a message between these two chains. And ideally, you have an app on each chain that is able to send and receive these messages. And then they have some sort of off chain verification. In this case, they call it DVNs. And these are these validator networks that they essentially make available for programmers to use for their source of verification. So if you are sending a message from one chain to another, it has to be verified by the DVN. And the good thing about DVNs in layer zero is that you can customize the level of verification. So if you would like to do things to make your transaction faster, normally the way that you'll try to do that is, I can't say changing finality, you can't change finality, but by thinking about what your viewpoint of finality is. So
Mhm.
normally you have to wait a certain number of confirmations before something is final. And in this case, you're normally waiting for the source chain's finality. So how long you have to wait will depend on the chains you're transacting in between. But let's say you are going from Ethereum to another chain, then you definitely would have to wait at least 12 to 15 minutes for finality. Or let's say you're going from a layer two, let's say you're going from Arbitrum to Optimism. Like Arbitrum is actually truly final after the 4-day window, 4-day proof window. So it's not as fast as a sequencer. However, depending on the application you build, you can actually customize this DVN and say, you know what, I am going to trust Arbitrum sequencer, and therefore I'm going to have this transaction verified on Optimism as soon as the sequencer set is verified.
So, Hyperlane and Layer 0 are very popular message passing protocols in the space. There are others as well, and I don't want to, like, exclude them. A lot of things integrated with Layer 0 and Hyperlane are multisigs, but I do want to point out that their protocols actually support things other than multisigs. It's just that not a lot of people use them. So,
Yeah.
yeah, I don't wanna call out anybody. But yeah, so Hyperlane works similarly. So instead of a DVN, Hyperlane uses what they call an ISM, which is an interchain security module, and it's serves a very similar purpose. Basically, in this ISM, an application defines how it wants to verify a cross-chain message. So it could be through a multisig, it could be through a TEE proof, it could be through a ZK proof, it could be through nothing if you really wanted to, but it's the same as layer 0. It allows the app to decide. And, yeah, so in Hyperlane, the flow is pretty much the same. You have an event on the source chain. Someone needs to listen for this event and make some proof for it, and then they submit this proof to the destination chain. That's kind of like a summary of both layer 0 and Hyperlane.
Yeah. I would say one thing they have in common is just the idea that you have to customize security. So as a developer,
Mhm.
you can think about which DVN you're going to listen to or how you're going to create your ISM. And then you have to think about speed and security. You
Mhm.
know that one of the attacks potentially to doing a cross chain transaction too quickly is if the source chain reorgs and that deposit transaction is no longer included, then you're minting something on the destination chain that actually should not be minted because it's not backed
Mhm.
by anything locked on the source chain. So in both cases, finality is definitely a concern. And that's why projects that try to push that forward are getting popular. Espresso aims to make it so that if the sequencer committed to a group of transactions, it definitely has to actually follow through with that. And that is done on the contract. So on the contract, it actually is checking to see if the sequencer is committing the same thing that they said they would commit on their own source chain. So
Mhm.
if the ISM module on their source chain that this deposit transaction was included, then the sequencer has to publish that to its parent chain as well for that layer two. So of course we're talking about layer twos here. I think that's something that we didn't actually clarify from the start. Like this is especially interesting for layer twos, and that's because layer twos get their security from a parent chain. Most times it's Ethereum. In this case, we're talking about Ethereum. So they have to publish their transactions to Ethereum as well. And that is seen as the source of truth. So yeah, I think that it's really interesting to see that finally everything boils down to finality.
Yeah, as always. And of course we're biased, but we mentioned how all of these proofs or these verification of messages need some sort of trusted source data. And this is basically what Espresso gives you. It says that this source data is trusted. You can use it to verify cross-chain messages. Yeah.
Yeah. And it's trusted because of things like being, behind a network, BFT fault tolerant. Of course,
Mhm.
eventually there would be proof of stake and slashing and all these things as well to even make that security more robust. But yeah, it's all about using customized security. And I think that is
Mhm.
probably one of the trends that we would see with the future of just verifying cross-chain messages and keeping it secure. I do think this customization makes sense because, like the example with ZK, if you are willing to wait 3 minutes and even pay a lot more for the transaction to be verified because you're transacting a lot of value, then you might say, yeah. But if you're playing a game or even just something that's like less important, you don't
Mhm.
want to wait that long. Like, there's no need. What do you see as like a trend?
Yeah. Well, what I hope is a trend, and I think this is good with modular designs, like Hyperlane, for example, is maybe an app starts out with a multisig because that's easy to bootstrap, it's cheap, etc. But as ZK proofs get cheaper and quicker, or as TEEs maybe get more accessible or something like that, they can switch their proof system without having to re-architect their entire system. And so I think that that's an important thing. And what I hope is that many multi-sig applications over time will switch their multi-sig to something that is more secure.
Yeah. Yeah, and I guess, like, we're talking a lot about security, and I think if you're a developer in this space, you are looking at the fact that there are these bridge hacks when you do cross-chain
Mhm.
messages, but at the same time there are companies telling you you should be cross-chain, and you're like, bro, like,
Mm.
I'm not trying to get my users funds hacked.
Yeah.
And but what we see in common is that the issues we're having here in Web3 are similar to that you'll have in any other company. Like, if you don't have good operational security, you could have things being leaked. So if you do start off
Mhm.
with a multi-sig, then make sure the security practices around it are sound. Like 23andMe, like people's DNA is all over the internet. Why? Why is it happening? It's operational security, and they're not even in complicated fields. I think blockchain is complicated. They're not in
Mhm.
complicated fields like blockchain. It's just like database security. I say
Mhm.
just, I'm not a DevOps, so please forgive me. But you know what I mean? Like, you just have to have good practices. And then on top of that, of course, the complexity does come in with these smart contracts. The code is completely public. So it's so much easier for people
Mhm.
to hack because they have time on their hands and everything is available. So when you are considering the security model that you choose for your application, I hope this podcast could help, like from this episode and previous episodes, where we shine lights on like the trust assumptions that are being,
Mhm.
made and what the differences are. And yeah, just hopefully projects like Aglia and Espresso and all these things can maybe help us, find a better solution.
In this episode, we covered how you verify cross-chain messages, and cross-chain messages are what bridges are based on. And we talked about several different ways. You have multi-sigs, you have light clients, you have TEE proofs, you have ZK proofs, etc. So my question out to everybody else is, does this change how you feel about using bridges today? Do you feel the same about using a bridge that is secured by a multi-sig? Maybe you do. Maybe you're totally fine with it. Or has it changed your opinion? We'd love to know.
Yeah. What about you? Has anything changed in your opinion?
I think, in my opinion, my view of TEEs has changed over time. Like, I'll admit it, at the beginning, I was like, "Oh, TEE kind of solves everything. Like, it's exactly the same as a ZK proof." I think over time, I've kind of realized that it solves some stuff, but not everything, actually. That's where my kind of understanding has evolved.
Yeah. Yeah. Okay, awesome. Yeah, let us know which security model you like best for cross-chain bridging. And please check out our previous episode where we talked about, are wrapped assets even real? See you in the next one.
See you. Bye. Hey, this is Ellie and Alysia. Thank you for joining us on another episode of Composable. We love hearing from you, so please hit us up on Twitter at ComposablePod, send us feedback, and join the conversation.
Our episodes go live every 2 weeks at 7 a.m. Eastern Time, so make sure you like and subscribe so you never miss an update, and you can even enjoy with your morning coffee. Share it with your friends and fellow builders.
We'll see you next time on Composable.